We know how to build highly capable single AI agents, but when you link those models together into an autonomous pipeline, the system frequently collapses. Researchers from Semri et al. Analyzed over 200 execution traces across major multi-agent frameworks. They found that 36.9% of pipeline failures stem from a single structural flaw, inter-agent misalignment. You see this first as work duplication. A research agent and a planning agent might independently execute the exact same API call, burning compute to retrieve data the system already has, simply because neither can see the other's active memory. Then comes inconsistent state. A billing agent confirms a user's payment, while a fulfillment agent simultaneously tells that same user their order is suspended for lack of funds. Both agents operate correctly based on the isolated facts they hold. This timeline demonstrates context dumping. To fix blind spots, developers pass entire conversation histories between agents on every turn, stacking them into a massive wall of text. This red line charts the result. Token consumption scales linearly, forcing downstream models to reread everything. Scaling multi-agent systems is a distributed system state problem. If your models do not share the exact same version of reality, they cannot collaborate. Designing a shared reality means stepping away from prompt engineering and confronting the hard constraints of systems architecture. This triangle represents the memory architecture trilemma constraints: latency, consistency, and cost. Enforcing strong consistency increases latency. Optimizing for speed risks stale data. Driving down costs requires aggressively pruning context. Pulling toward one vertex always pulls away from the other two. This diagram shows the simplest architectural response: centralized memory. Every agent reads and writes to a single monolithic database. The primary advantage here is perfect consistency. Because there is only one database, there is a single unified source of truth for the entire pipeline. But this architecture hits a hard scaling threshold. Past 5 concurrent agents, the model degrades. When 10 agents read and write simultaneously, the central store becomes a point of contention. Queue delays stack up, becoming a single point of failure. Relying on a monolithic store requires unsustainable compute overhead. Perfect state synchronization across dozens of models is simply too slow for production environments. The direct counter to centralization is distributed memory. Here, each agent maintains strict ownership over its own localized state. This model shatters the bottleneck entirely. It forces selective synchronization and enforces strict access controls between nodes. For highly sensitive environments, this model culminates in federated RAG. An orchestrating model queries a secure, isolated node and extracts only mathematical vector embeddings. The raw text documents never leave the local machine. Yet, this setup introduces a flaw native to decentralized networks: the trap of eventual consistency. Consider a billing agent that successfully updates a user subscription tier. If the synchronization protocol drops the payload or batches it on a 5-minute delay, that update is invisible to the rest of the network. Seconds later, a downstream support agent fields a request from that exact user. Because the network hasn't synced, the support agent operates on obsolete data. While distributed isolation protects data and scales horizontally, its vulnerability to stale state errors makes it too fragile to support highly interdependent workflows. To survive real workloads, engineers deploy a hybrid architecture. This is the current production standard. This grid diagrams how it works. A central orchestrator manages global state, while isolated memory layers are maintained for individual specialists across 4 specific levels: user, session, agent, and application. This structure relies on memory scoping to prevent context pollution. The operating principle is strict limitation. An agent must only ingest the context required to execute its function. Vector stores and key value caches are queried through intersecting dimensions, retrieving only the exact sliver of data where a specific user and agent align. As a result, a support agent retrieves a customer's service history without pulling in dense back-end billing logs. Yet both the support and billing agents can write critical updates back to the shared user profile without overwriting each other. This precision eliminates context dumping. Because agents no longer pass massive, redundant conversation histories back and forth, token consumption drops dramatically. Hybrid scoping balances the trilemma dynamically. By enforcing strict rules, it drives down latency and cost, preserving high consistency precisely where it matters most. Once a single multi-agent workflow is stable, The efficiency gains suggest a final scaling step, moving from a single user session to coordinating an entire population of agents. In standard deployments, agents solve complex problems through trial and error, but the moment a session ends, that successful trajectory is discarded. The next agent starts from zero. This network structure illustrates multi-agent transactive memory, or MATM. It is infrastructure built to permanently capture this procedural knowledge. Under MATM, producer agents log the exact steps taken to solve a problem, storing that proven pathway into a shared repository. Consumer agents facing similar tasks bypass rederivation entirely. They download that exact sequence and execute it without trial and error. This reveals the final architectural imperative. Memory engineering must be completed before you write your first line of agent code. If you fail to establish clear rules for state ownership, visibility, and conflict resolution, your agents will overwrite each other, drop context, and hallucinate facts. The difference between an experimental pipeline and a production system isn't the quality of the prompts. It is the integrity of the underlying architecture that governs their shared reality.